So we'll talk about what the thing is in IoT. So the Internet of Things is basically internet and thing, right? I mean, to be cheeky about it and silly about it, that's what it is. You've got some sort of device. That device is going to send data up to some sort of network address through some sort of protocol. It could be readings that it pulls periodically and looks at some electronics and says, yep, this thing is now this value, send it up. It could be anything you want to come up with, video streams. A button got clicked, right? Amazon's little button tools you can buy. And then ultimately, you want to be able to then have the thing on the internet, the server, help configure that device perhaps, send instructions to the device to turn something on or off, update itself, update its firmware. So basically, you take a device plus some sort of radio to connect to the internet and some sort of area on the internet, and that's IoT. It's kind of a marketing term. So it's a non-computer, right? I mean, a lot of things are little mini embedded computers that you use every day. But that's the point. It's like it's not a traditional computer, so they'll label that an IoT solution. Now, some of these solutions have processors that are really tiny, dedicated processors to do one thing at a time. And some of them have fully fledged computers on them. They can all be considered IoT for the purpose of this discussion. And there's many different ways to do this. You know, you can go to other cloud providers or actually go to servers that you put together yourself. This is, we're going to look at Amazon's way of doing it. So what are some of the things you probably use? Probably a lot of you have Nests or other thermostats out there, or you know, your automobile that calls back and sends stats. I have a Chevy Bolt, and so on the Chevy Bolt, I get a monthly thing that says, hey, you know, here were all the alarms that were set, which is hopefully none. And here's your tire pressure, and by the way, you went this many miles, it's time for service. That's because it's checking up. It's a little computer, and it's checking up with the internet and communicating with the OnStar service and letting it know. Tesla's same kind of thing. Teslas can send an update over to you and configure your device. Video doorbells. You know, in that case, now we're talking about more data, right? Because you're sending video, and you have to encode that video and send it across the network. So the type of thing you use, the hardware may scale upward to more like a computer to do that kind of task. Still IoT. You know, who has a fridge that's IoT enabled? Anyone? I don't. But anyway, and then you can, of course, build your own solutions. In our example, we're going to use temperature and light and humidity and pressure sensors and send that information up to the cloud. And again, these devices are supposed to interact with the world around them. So for example, these devices are meant to interact with electronics. So reading data from sensors, turning on or off different electrical circuits. You know, you can hook relays up, and a relay is just as an on-off switch, right? So you can have a relay connecting on and off power, house current level, or just, you know, low level voltage, whatever, and flip it on and off. You can turn motors, you know, lower and raise blinds, things like that, whatever. Adjust the speed and timing and things like that in a monitored machine. So maybe it's like a fuel mixture for a car and you want to adjust that. So anything you can think of, there's generally sensors or actuators, things that change things that exist for that. And I just grabbed a couple from our lab, and mostly I asked Don Coleman here for, what do you got? You know, I said, give me some toys. But these are some of the electronic devices, as an example, that could be wired up. And each device can be wired up differently depending on how it communicates. So this is, I believe, a sonar-based distance sensor, if I'm right. And it's sending a sonar echo and bouncing it back and recording how far something is from your device. Here's a temperature and humidity sensor. Here's one that does pressure as well, barometric pressure. So those are all sensors. And a couple things, sensors have various wire protocols or wire communications. So there are communications like UARTs, where you're actually communicating with a modem. There are communications like I2C and various GPIO, or general purpose digital and analog I/O communication signals. So depending on what you're connecting with signal-wise, you'll write code that actually reads and writes in that way. You're kind of almost like writing a device driver in a way. You're writing at a lower level. And then here are some examples of like, here's a switch, a motor. Can't really see the motor's paddle there, but for example, those are just some samples. So generally what you're going to end up doing is put together a solution that has some sort of processor that communicates with hardware and then sends information back and forth to the internet, IoT. There's a couple things you have to keep in mind. First of all, do you need this thing to be on battery power? Maybe you're putting together a solution that's not going to be able to easily get 120 volt current. Needs to sit out for a long time in some sort of remote location. You know, so in that case, it may be battery powered. So what type of processor you choose and what type of solution you choose and how often you wake it up to gather the data will vary. So that all goes into your ultimate final selected solution for this IoT project. What kind of bandwidth, right? We talked about the video device, like a video doorbell, or Deep Lens from Amazon, which is like their video recognition device. Those things have to encode video, and that takes a lot of processing power. That's probably not going to be something that's going to live on a battery and sit out there in the field for 3 months. Are you intermittently connected? You know, maybe you're in some sort of vehicle and sometimes it goes under a bridge and it's not connected anymore, and your code needs to handle reconnecting if it's not connected anymore. Or maybe also related to battery power, you need to shut it down because you don't want it to read the sensor every three milliseconds, you want it to read every hour, right? That all goes into your choice. And in some cases, connection coverage might be difficult because of the physical location of the device. You know, maybe there is no good Wi-Fi connectivity in the warehouse or a basement or some sort of room, but it can get to another device in your same network, and that can then get to the internet, a so-called edge device. So that's another option. You put a bunch of sensors in a mesh, you know, devices in a mesh, and the edge of the mesh can communicate up, and that's a potential solution. So these are all factors that go into your design of the devices and how they connect. Your main inflection point in terms of the physical devices is whether you choose a microcontroller-based device or something that's like a single board computer. And again, for video encoding, you probably need a single board computer because you need something, and I'd say probably because they're always scaling up the performance of these microcontrollers and what they can do. But let's just assume for now that that's an inflection point, that you either have to have an operating system, multitasking, programming in a higher language, like maybe you want to program it in Python, you know, or JavaScript or Java or something like that. A little bit of a stretch depending. But single board computers can do that. And as an example of those, if you've ever experimented with an Arduino, with a Raspberry Pi is one of those single board computers. It has a fully fledged operating system, gigabytes of RAM, you know, and multitasking and all of that, and persistent storage in a file system. That's on the heavier end of IoT. On the lighter weight end, where you're talking about battery connected devices that live, you know, in the field for a long time or just have low power, then you have microcontrollers. And microcontrollers are dedicated single task at a time systems. They're going to be, you're writing a particular program you're going to mount on it. Usually you write it in C. If you used an Arduino before, that's an example of a microcontroller. And Arduinos, you send the code to the Arduino and it runs as basically a compiled C program. And there's no operating system. There's no real file system. There's none of that stuff. You've got kilobytes to a megabyte or two or whatever of memory. You don't have a file system directly. You have to write calls to some API to write to your file system based on what board you bought, right, to write and read files. So you can do it, but you're programming everything at a lower level. But because of that, you can buy some of these. They have a real-time clock in some cases. You just say, go to sleep for an hour. And when you wake up, resume what you're doing. And then when you're done with the cycle, the loop of reading everything and sending it up, go to sleep again. Wake up in another hour, and so on. And that takes a lot less power, especially if the radio is turned off until you wake up. So these are all things you can do with a microcontroller a lot easier than if you're running Raspberry Pi and say, hey, let's shut down the operating system for an hour. Not so much. Okay, so they don't always have the low power on-off ability that a microcontroller does. Does this make sense in terms of the differences between the two? So that's why you would choose something like a single board computer with an actual operating system versus a microcontroller. You have a single purpose in the field, low power device that needs to do something periodically and doesn't have to do something really complex like encoding video or multitasking. microcontroller. More sophisticated stuff, single board computer. We are going to use one of these in the field today at 2 o'clock for people who are going to be in the workshop. We are using an Arduino called the Maker 1010, and this is a single board microcontroller based solution. It actually has 3 microcontrollers on it. It has one for networking. It has one for encryption. There's actually an encryption microcontroller in there specifically for encoding encryption keys and for encoding and decoding data. But the main processor is the SAMD21 Cortex M0 Plus Gesundheit. So that is an ARM-based processor that will run little C programs for you. And we're doing that through the Arduino SDK and the Arduino IDE. So that's the example of what we're going to do. It gives you the ability, you can't really see it very well in this picture, but this, I'm just going to zoom in a little bit. These little things on the right, which are barely visible right now, are little headers. They're pins. And they can communicate with analog and digital devices. The idea of these boards, and even with Raspberry Pis, is they are very easy to wire in and communicate electrically with different things. A regular PC can't do that very easily without adding additional hardware. These things come with the general purpose I/O pins built into them, generally. We are also going to use something called a shield. Now, a shield in the Arduino parlance is a board you can plug on top of those headers in the same pin locations, and it automatically mounts things you would have to solder together yourself on a breadboard. So they make a compatible, they make a couple of devices, but they make a compatible device with this that's called the Maker ENV, and that one has environmental sensors. So on this one little board you're going to get today, you have an SD card reader and writer, which we're not using for the experiments, but that's there. You have an atmospheric pressure sensor, a temperature and humidity sensor, an luminescence sensor, how bright is it in the room, and you've got UV A and B. And then there's a reset button that goes through where you can't get to the reset button because you've covered it. So that's an example of a shield where you don't have to solder everything together, and it gives you some things you can experiment with right away as you're prototyping. This is the shield stacked on top of the Arduino. Literally plugs into the same pins, and now it's connected up. You could still access the pins it's not using. So I think it takes over the LED pin, for example, so you have to use something else for the default LED. But if you want to use one of the general purpose I/O pins, you could do that, as long as you're not using one of the ones that it's using. And in this example, we have it wired up with an LED, and in the wrong location, Don would say pin 6, which he moves to pin 5, I think, in his experience. Now, I'm going to get into more detail about this diagram later, but I just wanted to kind of point out that when we get to actually communicating with the servers, with IoT Core in our case, so over here is Amazon's IoT Core, it's going to implement something called a message broker. All right, and Don's going to talk about the protocol called MQTT, which is what it communicates with, as one of its options. So over here, all you have to do is connect to the internet and use MQTT. Don's going to talk about all the physical transports of configuring a device to talk on an internet. On the internet, apparently there's more than one. And then basically you're going to be communicating with TCP/IP. In general, it's a regular networking protocol. You've got a network address on the internet for however long you're connected, and you're communicating up and sending a message, in this case through something called MQTT. It could even be a REST endpoint. So it depends on what you want to do. Amazon supports that as well. What we'll talk about in my second talk is there's encryption that has to happen. So if you've ever used a secure website, you've used something called TLS. It used to be called SSL, but TLS, transport layer something or other, something, service encryption. It's an encryption mechanism using basically X509 certificates. And so you've used this before every time you shop. And if you've ever set up a server, you signed certificate requests and you've created a server cert from a request. You have to do the same thing from the device because the device doesn't have a login and password dialog, right? And that's kind of dangerous to put that on a console on a device and have to type it in. So you want it to be something where it's private to the device. It's a certificate that is generated from a private key only the device knows, It connects up, and then through this TLS encryption, Amazon and it can handshake, and they can communicate in an encrypted way. So we'll talk about all the details here in my talk after the break. But bottom line is there's a certificate for the device, and there's also a certificate for Amazon, and they're used in the handshaking process. And that's a pretty standard mechanism for communicating. The nice part about that is once you create the certificate and install the certificate and make Amazon aware of it, now whenever a message comes from that device, as long as you're sending encrypted traffic, it says, oh yeah, that's the device that represents this physical border. And then you can associate it with a location, whatever else you want to do. So it knows where the device, what it is. And you can secure based on that. One little note here, it is very easy to go in and use tools and say, oh, I need a key pair. So let me generate a key in a certificate. Oh, thanks, now I have one. I'll put the same cert on every single device in my network. That's cool. So now what problem that poses for you is, every device in the network looks like the same device. And let's say someone hacks that key and puts it on their computer and starts acting like your device. Well, now you have to write out one key and kill it. You've just killed all your devices. So in general, each thing should have its own certificate and key. It's the one warning I have for you there. All right. So again, IoT, Internet of Things, is just a marketing term. You know, it could be anything, but it's generally any kind of device plus a radio plus the internet is an IoT solution, logically speaking. Usually I don't want to always say things like usually and things like that, but they are generally devices that are lower power. So in many cases, these IoT devices, because they can use lower power chips, are going to use microprocessors as opposed to full-fledged CPUs. And they interact with sensors and actuators and things like that to view and control their environment, and they can communicate up with a server like Amazon. All right, Don has a great talk that's a much more involved talk. It goes into the history of IoT, and so it's called WTF IoT or IoT for the win. And we'll post notes to this. We'll have a link that we'll send out that'll have some resources for you, and there's a paper we're going to hand out today as well. But that'll be something you'll be able to look up and view. All right.